Hi everybody, this is the class notes on predicting products of chemical reactions. So if you aren't already there, go ahead and open up your notes packet to 11.2, and just after that section you'll find a section for class notes. And what I want you to do first is actually write these titles in that section. Make 3 columns like this. So reaction type, and these are the 5 reactions that we've gone over. We're going to go through each one of those again. So synthesis, decomposition, single replacement, double replacement, and combustion all have to fit here. So if you have large handwriting, you might want to try writing a little bit smaller today. Recognizing the reactants and then predicting the products. So the goal here is, if I give you something before an arrow and I don't give you what comes after the arrow, you will be able to tell me what will come after the arrow, no matter what kind of reaction it is. Now, the first step to doing that is actually recognizing the type of reaction. Otherwise, you have no idea what's happening and you don't know what's going to come after the arrow, other than the fact that it'll still have all the same elements. Okay, so we'll start with our very first type of reaction that we learned in 11.2, and that was a synthesis or a combination reaction. Okay, so when you are looking at a synthesis reaction, you are looking at just 2 elements before the arrow. So all that there is before the arrow when I'm asking you to predict the products is going to be 2 single elements. Okay? The only thing 2 elements can do with each other is form a compound. And so the predicting products after the arrow is going to be a compound made of those elements. So if I wanted to give you an example of this, if you were looking at a reaction and you had magnesium plus nitrogen, okay, and remember nitrogen is diatomic, so that's going to look like that, okay, and then, all we have is the arrow, and you have to fill in what comes after the arrow. Well, you have to put those 2 together to make a compound. Now, balancing the charges is key, so this is a really important piece. Whenever you're putting together a compound, you're going to have to balance the charges. If you look at the periodic table, magnesium is a +2. Nitrogen, when it becomes an anion, is a -3. So in order to get those 2 to balance correctly, you're going to have to do Mg3N2. Okay? Now that's the product, and then after you've written the product, that's when you go back and you look at balancing the entire equation. So for this example, my nitrogens are balanced, okay, because magnesium was a +2, so it happened to keep my 2 nitrogens. But the magnesium is not balanced, so I would have to come over here and put a 3 in front of magnesium. Okay, so that's an example of a synthesis reaction that I would give you just the 2 elements before the arrow. You have to recognize that that's synthesis, put those elements together in the correct proportion, and create the compound as the product. Alright, so I'm going to erase that one, and we'll go into our next reaction type. Okay, so next reaction type was the opposite. We had decomposition. Okay, I'm going to cover up that little side note there. So, decomposition, all you have before the arrow is a single compound. If all you have is a single compound, the only thing that it can do is fall apart. And we're going to try and keep this simple when we're predicting products. It's going to fall apart into the elements that it's made out of, okay? And then you're going to have to make sure that you remember to recognize your diatomics. So if I'm thinking of an example from the book, we had HI and then an arrow. So again, if all you have before the arrow is a compound, then it has to split apart. That's all it can do. There's nothing else that's going to happen with that, okay? So it's going to split apart into its elements. Now, if you do H plus I, you're at least recognizing that it is decomposition. But you have to remember, hydrogen ends in gen, iodine ends in INE. Anything that ends in gen or ene is going to have, or is going to be a diatomic element, and you're going to have to remember to put in those subscripts to indicate that they are paired with themselves in their pure form. Okay? Then you'll have to come back over here to balance your reaction and put a 2 in front of HI. So that's an example of a decomposition with a binary compound. So remember, binary is made of 2 elements, decomposing into its elements. Okay? Now, there's a special example of decomposition that we're going to have, and if you can remember special things, sometimes you can get extra credit. So I'll try to click out of this so you can't see that. Okay, so special process for carbonates. So if you remember that a carbonate is CO3 2-. So anything that's bonded with carbonate has a typical decomposition pattern, and it'll split into carbon dioxide and a metal oxide. Now I'm going to give you a couple of examples of this so that you can see that. Okay, let me just come down here a little bit. So if I have, for example, a magnesium carbonate, so this would be magnesium carbonate, and that's all I have before the arrow, then it's going to look like this. Okay. Now, if you can memorize that carbonate is going to always fall apart into CO2 and a metal oxide. The metal is whatever was with carbonate. So magnesium is my metal in this case, and magnesium is going to bind with oxygen to form the metal oxide. Now, it just so happens that carbonate's a -2, oxide's a -2. So if there was one magnesium with the carbonate, there's one magnesium for every one oxide, and that's what we end up with. And these are always going to be balanced at the end. Okay. There is one other example of a carbonate decomposing that I want to talk about. It's not really a metal oxide, but this is the substance that is found in, hang on a second, I lost my navigation here. Okay. That is found in your carbonated beverages. It's called carbonic acid because carbonate, 8 becomes ic when we do acid names, so that's carbonic acid. Now when you open the soda and you release the pressure inside, you're going to end up with the bubbles coming out of your soda, and those are CO2. Okay, so remember, carbonate always decomposes into carbon dioxide. Okay, and then your other product in this case, instead of a metal oxide, is going to be hydrogen with oxide, and 2 hydrogens with an oxide is H2O. So when your soda goes flat, all of the carbonic acid has converted into carbon dioxide and H2O, and all that CO2 has left the soda when it becomes flat. And literally, your soda is more watered down. And so if you've ever noticed that when something has gone flat, it tastes more watered down, that's actually true. Chemically, you have created a lot of water in there that wasn't there before, and your soda is a little bit watered down. Okay, so that's decomposition. We'll delete this and we'll move on to our next type of reaction. Okay, so we get a little bit more complicated when we get to single replacement. Okay, you're going to have one element and one compound before the arrow. And that element is not going to be oxygen 99.9% of the time. I mean, I could probably figure out a single replacement with oxygen, but we're going to be working with a compound and an element. And our compound is going to be dissolved in water, and our element is typically going to be a solid, but it could be a gas as well. And what we're going to end up doing, remember, this is like the couple dancing and a single guy cutting in. Okay? So what's going to happen is this element, the single guy, is going to steal a partner from the compound. And you're going to get a new element by itself, kicked out, his girlfriend stolen, okay, and then a new compound, so a new couple dancing. You need to use the activity series to make sure that the reaction will actually happen, and you need to balance charges. Now the book has an activity series, but it's not very complete. What you should do is use the activity series on the back of your Plainsman periodic table. It is much better, and it will help you with these reactions. Okay, so to do a couple of examples for you. If I have magnesium and silver nitrate, okay, that's all I have before the arrow. The first step, again, is recognizing that this is a single replacement. So I have magnesium, a single element, and then I have silver nitrate, which is a compound. Silver is the cation, nitrate is the anion. Okay, so magnesium, because it's a metal, it wants to replace metals or hydrogen from the compound. Okay, and so whatever that first substance or first element is in the compound is going to be replaced by my magnesium. Now, if you look at your activity series on the back of your periodic table, go ahead, look at it. Find magnesium and find silver. The only way that this reaction can happen is if magnesium is more reactive than silver. Otherwise, silver is going to say, no way, you can't steal my partner. You're not reactive enough. Okay? And in this case, magnesium is much higher on the activity series than silver, so it will steal silver's partner, which is going to leave silver on its own on this side of the arrow, and magnesium nitrate is going to be the other product. But you have to remember to balance charges. This is key to getting these reactions right. Magnesium is a +2. Nitrate is a -1. So we have to have 2 nitrates for every magnesium in order to balance those charges. Okay, so that is the correct product. And then to go back and balance the entire reaction, over here we have 2 nitrates, over here we only have 1. So we need to put a 2 in front of silver nitrate, and then we have to put a 2 in front of silver to balance the silver. Okay, so that's one example. If I gave you another example that looked like this, copper, whoops, let me get out of that. Copper plus sodium chloride. Oops. Okay. Again, always use your activity series, and you want to look at that, and you're going to see that sodium is much more reactive than copper. Copper is way down towards the bottom, sodium towards the top. Copper is not reactive enough to steal sodium's partner, and so this reaction will not happen, and we would put NR for no reaction. Okay. One more quick example before we finish this up is going to be with nonmetals. So if I have fluorine, okay, that's a nonmetal. It's still an element, even though there's a 2 there, okay, a diatomic element. It's still just a single element, and sodium chloride. Okay. Now in this one, because my single element is a nonmetal, it's not trying to kick sodium out of the compound. It's trying to kick chloride out of the compound and steal sodium. Okay, so you want to make sure that you pay attention to that. A nonmetal, other than hydrogen, because hydrogen's over on the left, it's going to act as a positive cation. Okay, but nonmetals that act as anions are going to kick out the anion in the compound. So fluorine is going to try and kick out chlorine in this compound. Okay, and if you look at the activity series towards the bottom, there's a section of the activity series for nonmetals. It has all of our halogens in there, and we can see fluorine is much more reactive than chlorine. Okay, it's at the top of the list. So chlorine is going to get kicked out by itself, and we're going to have sodium fluoride as our other product. And then we have to go back and balance the fluorine and the chlorine based on the number of atoms on each side. Now remember, balance charges first, and then think about balancing your reaction. So we'll end up with a 2 in front of sodium fluoride and a 2 in front of sodium chloride. Okay? Alright, that's single replacements. Those ones you have to use the activity series for, and that's the only ones you have to use the activity series for. Do not use it for any other type of reaction, especially not the next one. Okay? Double replacement reactions are going to be 2 aqueous compounds before the arrow. And that's the only type of reaction that has 2 compounds before the arrow. So if we look at this, 2 single elements, a single compound, a compound and an element, this is the only time we have 2 compounds before the arrow. Okay? So 2 compounds before the arrow is automatically a double replacement, and they're going to trade cations to make 2 new compounds. One of those is going to be aqueous, one of them will be solid, liquid, or gas. And we're going to do some practice with this and some solubility rules and physical states notes next week, so you'll be better at figuring out which one is aqueous and which one is solid, liquid, or gas once we get to next week. Okay? But our 2 aqueous compounds trading partners. Alright, so good example of this one. Let's do copper 2 chloride and sodium hydroxide. Okay? So again, when you see 2 compounds, automatically double replacement, we're going to trade cations. So here I have copper as a cation, here I have sodium as a cation. I'm going to swap those out. So now sodium and chloride are going to become partners, and copper and hydroxide are going to become partners. So 2 couples dancing, they trade partners. Balance the charges. I'm surprised I didn't write that over here. If you want to write it again, just it helps to be totally redundant here, but balance your charges. It's important. Okay? Sodium's a +1, chloride's a -1. So those 2 go together, 1-to-1 ratio, sodium chloride. Okay? Copper can be more than one charge, and we can't tell just by looking at the periodic table, But if you look at this, it has 2 chlorides with it. That 2 came from the copper's charge. So copper in this equation is a +2 charge. Hydroxide's a -1. So because of that, we have to put that hydroxide in parentheses and put a little 2 on the outside to say we have 2 hydroxides for every copper. So those are my products, and then I have to balance. Copper is balanced. Chloride, there's 2 here, only 1 over here, so I have to put a 2 in front of sodium chloride. Okay. Now sodium, there's 1 over here, 2 over here, so I have to put a 2 in front of sodium. And then 2 hydroxides because of that 2 in front, and 2 hydroxides because of that 2 outside the parentheses, so that one's balanced. Okay, so double replacement is probably the most work as far as having to put 2 compounds together and balance their charges, but we're just trading cations and creating the 2 new compounds on the other side. Okay, if you recognize one of those compounds, like this one, table salt, we know that dissolves in water, so we're going to know that's our aqueous compound, because aqueous means dissolved in water. Okay, the copper hydroxide is going to be a solid precipitate, and again, we're going to learn those rules next week. Okay, our final type of reaction is going to be combustion. Okay, combustion. And we're working again with combustion of hydrocarbons. So this is the general equation or thing you're going to look for before the arrow. A hydrocarbon fuel, remember hydrocarbon is made out of hydrogen and carbon. Okay, so it might have other elements, but it definitely has to have those. And oxygen. So these, remember up here we said a compound and an element that is not oxygen, that's a single replacement. But if your single element is oxygen, now we have a compound with oxygen, that's a combustion. And these are the easiest ones to write the products for because they're always CO2 and H2O. Okay, and they're both gases because we're going to have a high temperature, and that's going to make that water come out as a gas instead of a liquid. So again, hydrocarbon fuel plus oxygen, combustion, and you always write CO2 and water as the products. That's all you have to do, okay? So the hardest part about these ones is just recognizing that you have a combustion. So let me expand this up just a little bit so you can see this, okay? Okay, so back to an example here. If I have CH4, this is methane, that's what we burn in our Bunsen burners, okay, and O2. So this is all you're given before the arrow. You have to figure out what comes after it. Just the biggest catch is making sure you don't see this and think single replacement. Okay, oxygen is not going to be the single element in a single replacement. Okay, it will not do that. It's going to rip this molecule apart and combine with both pieces to make 2 new products. So oxygen is going to combine with carbon to make carbon dioxide. Oxygen is going to combine with hydrogen to make water. And then after you've written carbon dioxide and water, that's when you go back and balance. So again, when you see oxygen before the arrow and it's with a carbon compound, this is combustion, and you automatically write, oops, CO2 and H2O. Not CO at, let's do CO2 and H2O. Okay? And then you can go back and balance. So carbon, carbon, balanced. 4 hydrogens, 2 hydrogens, so I need to put 2 in front of our water over here. That gives me 4. Okay, and then 2 oxygens over here. Right now I have 4 oxygens on this side, 2 for the water and 2 from the CO2. So I need to go back and put a 2 in front of oxygen here to make it balanced. Okay, so I hope this was helpful. I'm sorry I couldn't be there with you, but hopefully we can use this tool again in the future when we are learning or reviewing our stuff for our final exam. Okay, feel free to watch this again. It's on YouTube, but I hope you can practice with this with the Predicting Products worksheet, and I will definitely see you next week, and we can get all of our worries worked out, and we'll practice a lot with this next week before we take a quiz on Chapter 11. Okay? Thanks, everybody. Have a great day.